This is the video on forces. So remember, in these videos, there will be two codes. One will be a written code on the screen. The other will be a verbal code said by myself at some point during the video. You do need these codes to move on. Now, or move on without any homework assignment. Now, let's just, when you're looking at these slides or watching these videos, what's in green, you can make a nice little bulleted list that can go into your notebook. The rest is just good information just to keep a good, like a solid idea or little extra information to help you out. So, weekly, this is the written code. I would recommend you write this down somewhere. All right. So here's an original question. What forces are acting on you right now? So just right now, just sort of think like what forces, like what is acting on you right now? When you're doing this, like just think about, well, what is a force? What is pushing or pulling on you, right? So that is what a force is. A force is just a push or a pull in a given direction. Force is a vector quantity, which means it has both magnitude and direction. The unit for force is the Newton, and it's represented by a capital N. Now, we represent a force by a line with an arrow to indicate the magnitude and direction of the force. So there are 6 different forces that we're going to learn about in this class. Number 1 is Fg. That's the force of gravity or weight. Fn, that's a normal force. It's the perpendicular support force. This is the one that students forget about the most because if you're just standing there, you think, well, obviously gravity's pulling on me. That's my weight. But if you're not falling down to the center of the earth, something's supporting you. Something's providing that normal force, that perpendicular support force on you. And that's what normal means. In mathematical terms, it means perpendicular. Fa is the applied force. That's from a person or object onto another person or object that attempts to change the motion of the object. Ff is the frictional force, which opposes a sliding motion. Fd is drag or air resistance. I've also seen this written as, air, like air resistance. I write it as D just because I want that one letter. But we just say drag. It's fluid resistance that opposes motion through a fluid. And Ft, this is from a rope, string, or a spring. So these are the 6 forces we're really going to be concerned with. I've seen sometimes Ft, the tension, they add a 7th one, a spring force. I just combine them into one just to make it easier. So now let's talk about net force. Forces can add to each other, right? Think about pushing a car. If one person is pushing in one direction and another person is pushing in the opposite directions, those forces aren't helping each other out. Those people aren't helping each other. If they're pushing in the same direction, those forces will add. So this is called the net force. The net force is the sum of all forces acting on an object. So you can see here that I've got, this person pushing an object, this person pulling an object. If they're pushing and pulling in the same direction, those forces are going to add, and we're going to get a net force. So this is an example, right? So force is a vector, which means it has a direction. Adding the forces together doesn't necessarily mean that net force will increase. Sometimes the force can be applied in the negative direction or the opposite direction. So let's just take a look at this. If you see somebody's car broken down, you see them pushing on it, you're obviously going to go up and push that car in the same direction. Yeah, you're going to have a net force. Now, if you go up and you see somebody pushing on a car and then you decide to be mean and push in the opposite direction, well, if you're pushing at about the same strength, well, the net force is 0 newtons. You're not helping that person out. You're pushing against that person. And you can have something weird like at angles and then you've got friction, but we're not going to concern ourselves with that. We're just going to make sure that you understand that a force is a vector quantity. When you add them together, well, that doesn't necessarily mean they're getting bigger because you can be going in the negative direction or the opposite direction. So now let's talk about balanced versus unbalanced forces. So balanced forces it is what it sounds like. All the forces are going to cancel out. The net force on that object is 0 newtons. The object is at rest or at a constant velocity in the straight line. Now, unbalanced forces, all the forces do not cancel out. The net force is not 0 newtons, and the object is accelerating. So this is going to be key. This is going to come up a lot in physics, especially when you get to Newton's laws. Net forces, right? Those unbalanced forces cause acceleration. If there is an acceleration, then there is an unbalanced force. So I like to think of astronauts out in space, right? That way we can remove gravity, air resistance, friction here on Earth. Just think about an astronaut floating. Well, there's no forces acting on this astronaut. The net force is 0 newtons. Now, If an astronaut is moving, there can still be a net force of 0 newtons. That astronaut is just traveling at a constant velocity. Nothing's pushing, pulling on that astronaut. Astronaut's just traveling. Now, if those astronauts were to get into a ship and turn the engine on, well, then you're going to have an applied force. That object, not only will it be moving, but you're going to have a net force acting on it, an unbalanced force, which will cause that spaceship to accelerate. So let's take a look at a couple of examples, right? Let's take a look at kicking a football, right? So which forces are being applied? Just think about that, right? So if I'm looking at this football right now, I know it's at rest, which means the net force is 0 and the forces are going to be balanced. So I'm going to have gravity being applied to it because we are here on planet Earth. I'm going to have the normal force because it's not falling down to the center of the earth. That ground is supporting it. And you can make an argument. There's a small applied force as he's holding this football. He might be pushing down a little bit. But if I add up all these forces, the net force is going to be 0 newtons. The forces are balanced. This object is not accelerating. Now let's take a look as the kicker is kicking it, right? So think about what object or what forces are being applied. Now, obviously, this football is accelerating now, which means the net force is not 0. There will be a net force acting on it, and the forces will be unbalanced because this object is accelerating. So I'm still on planet Earth. Gravity is still pulling down, but now I'm going to have an applied force. That's what the kicker is doing, applying a very large force. I don't have a normal force because it's not on the ground. It's not being supported. And this is going to be my net force. It will be accelerating in that direction. And yes, you can make an argument for maybe drag. There might be some air resistance as it's moving. I didn't put it there. Now, let's take a look after now the football is going through the air. The kicker has stopped kicking it now, right? So think about what's being applied to it. Now, this one's kind of tricky. This object will be accelerating, right? And it's because, gravity's pulling it down. The net force will be not 0, right? There will be a net force accelerating this object, and the forces are unbalanced. You have a net force, right? The net force is not 0. So this is what I mean by that. You're going to have gravity pulling down, and you're going to have a drag force as it's going through the air. Notice these aren't balanced. You will have a net force going in this direction, and the football will be accelerating in that direction. Let's take a look at another example, a deadlift, right? Let's just say the barbell is at rest on the ground. The net force is 0. The forces are balanced because the object's at rest. Now, let's just say he's lifting it up off the ground and it's moving at a constant velocity. The net force is still 0. The forces are still balanced because it's traveling at a constant velocity. Now, the instant he lifts it up, it goes from rest to moving. Yeah, there will be a small acceleration. There will be a net force the instant he lifts it, but not as he's moving up at a constant velocity. Now, once he lets go, right, he just lets go of the barbell's falling down, the net force is going to be not 0. It's not 0 because the forces are going to be unbalanced. That object is accelerating down. That barbell is accelerating. So how do we represent forces? Free body diagrams, right? Forces acting on an object can be represented by a free body diagram or FBD. Now, here are the following steps to make a free body diagram. You draw a dot representing the center of mass of the object. Draw arrows pointing away from the dot representing the forces. The arrows should be scaled. Label the forces. Real easy. So let's get some practice, right? Let's take a look at a dog pushing a wheelchair at a constant velocity, right? So we think about the forces. We know that if it's at a constant velocity, there's not going to be a net force. The net force is 0 newtons, and the forces are balanced, right? So let's take a look at those forces that are going to be acting on this, right? So I've got a gravitational force, normal force. Those balance out, right? Gravity's pulling down, normal force going up. You're going to have an applied force. The dog is applying that force. Now, what's going to keep it going instead of not going at a always accelerating? There's going to be a frictional force on those axles that'll keep it. Now, the net force is 0 newtons because it's traveling at a constant velocity. This is what my free body diagram will look like. Notice that they're all balanced out. Now, let's take a look at a horse skidding to a stop. So slowing down, that should instantly in your mind say, oh, this horse is accelerating because it's slowing down. So let's take a look at the the forces that are being applied to it. Obviously, we're still on the planet Earth. Gravity is pulling down. Normal force is supporting this horse. What's slowing it down is a frictional force. Now, this horse is moving to the right, but there's no force that's propelling it to the right because it's slowing down. I have a net force going in the opposite direction. That is what is slowing this horse down. This is what my free body diagram is going to look like. So let's take a look at a skydiver at a terminal velocity. So terminal velocity means constant velocity. So let's take a look at those forces. So I'm going to have gravity pulling down. Right now the forces are unbalanced, but constant velocity should jump out at your head saying, oh, these forces need to be balanced. The net force needs to be 0 newtons. So the drag, that air resistance is going to balance out gravity. Once you get going fast enough, yeah, you're going to have enough air resistance. Think about sticking your hand out the window. You're going to feel that air resistance. The net force is 0 newtons. This is what my free body diagram will look like. Yes, that skydiver is moving down really fast, but the forces are balanced, right? They're traveling at a constant velocity. All right, now let's take a look at a bowling ball traveling down an alley at a constant speed in a straight line. So let's take a look and see what forces are acting on it. Well, I've got gravity and I've got normal. Yeah, I don't really have much, like really any friction because it's just rolling down this slick track. Net force is 0 newtons. This is going to be my free body diagram. I've got gravity and I've got a normal force. Now, this one is a little bit different. We do have a bowling ball, a hook shot. So now it's traveling at a constant speed but curving. So remember, 3 ways to accelerate: speed up, slow down, turn. Because this bowling ball is turning, it is accelerating. So there will be a net force, and the forces are unbalanced. So let's take a look at what's causing that. So now I've got gravity down, of course, normal force supporting it. It's not falling down to the center of the earth. And what's going to do is that ball spins, there's going to be a frictional force, and my net force is going to curve it in the direction of the pin. So this is what my free body diagram will look like for a bowling ball hook shot. So we did a few activities, right? We did the balanced forces versus unbalanced forces. Now, when you're doing this, right, this one was just doing the first one. This one is looking at forces saying, hey, is it balanced, unbalanced? Reading the scenario and being able to say, okay, well, is it balanced, unbalanced, and is it speeding up, slowing down, or constant speed? Now, at this time, I'll go ahead and give you that verbal code. The verbal code is 114. I say that again. The verbal code is 114. Then we did match that free body diagram. So in this one, you looked at a scenario. The scenario is given to you, and you click through to find the free body diagram that matched that scenario. Last class activity we did was the net force, calculating the net force of an object, determining whether those forces are balanced or not, and whether that object is accelerating or not. So just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.